Hello, this is Mark Pinion, and this is Lab 5, the Choose Your Own Adventure Lab. For my lab, I chose to look at the motion of Felix Baumgartner as he jumped in an attempt to break some world records. In his jump, Felix aimed to make the longest free-fall jump made by a man, as well as be the first man to break the speed of sound outside of an aircraft. Through my computational model and analysis of Felix's motion, I was able to make interesting observations concerning Newton's second law, drag force, and terminal velocity. In my analysis, I observed that both terminal velocity and drag force vary with altitude due to changes in air density. Also worthy of note was the observation that Felix exceeded terminal velocity for a good portion of his flight. Major principles used in this lab include Newton's second law, the formula for drag force, as well as the conditions that cause terminal velocity. Unlike in Lab 2, we include the fluid density, rho, in the drag equation, as the air density varies significantly throughout the atmosphere. This variable air density causes a variable terminal velocity as well, and helps us build Felix's terminal velocity profile. The data used to set up this profile was gathered by a weather balloon sent up with Felix. Air pressure and temperature data was sent to scientists on the ground who constructed the terminal velocity profile. In my lab, I had to make some simplifications and approximations for the sake of time and simplicity. The first simplification concerns the proportionality constant B in the drag equation. I combined the air density and 1/2 factor from the drag equation into B in order to make the drag equation easier to manipulate in my code. I determined the value of B by trial and error until my model lined up relatively well with the observational data. The second approximation is a result of my time intervals. I got data every 2 seconds for Felix's jump, so this can cause slight inaccuracies, but nothing major. The final simplification I made was assuming that Felix's motion was straight down towards the Earth in the negative y direction. This made motion analysis much easier. I gathered my experimental data from a YouTube video that had the data concerning Felix's flight. I then exported this data to VPython in the form of a CSV file. To build my computational model, I built off of the Lab 2 skeleton code, altering initial conditions to mimic Felix's mass and initial altitude. I also changed how drag was calculated, although I will discuss this later. Here is the computational model in action. The yellow arrow represents weight force, and the blue drag force. The blue sphere represents the model's prediction, and the red represents the observational data. The green sphere pictured represents the ground. The model does a relatively good job of predicting Felix's complicated motion for the beginning part of the falling, but soon differences begin to occur. The model ends up under-predicting his position by a significant margin, but this is understandable as his motion is quite complicated. The graph on the right, comparing the predicted velocity versus the actual velocity, lines up pretty closely, but due to the rapidly changing fluid density, I can only get a rough fit. The underprediction of the final position comes about because of the underpredicted velocity, which in turn is caused by an overprediction on the drag force. In my analysis and model, I used the formula for turbulent drag, which relates the drag force to the square of the velocity as well as the fluid density of the medium. As Felix fell and the air became colder and more dense, the drag force increased. Another interesting thing to note is that for the first 20 seconds, Felix experienced no drag, as there was little to no atmosphere and therefore little to no air to act upon him. To implement this changing density in my code, I changed the value of B, the proportionality constant, as time went on. Since I included fluid density in my B calculation, I only needed to change one variable to account for changes in the fluid density. Regarding terminal velocity, Felix was actually able to exceed it during his jump. This was possible because of the relationship between Felix's rate of change of velocity with respect to time, or dv dt, and the change in projected terminal velocity versus altitude, or d velocity terminal over dA. Since Felix's projected terminal velocity was changing faster than his velocity, he temporarily surpassed this velocity on his way down. A good way to visualize this situation is to think about moving from very hot and not so dense air to very cold and dense air in an instant. Your momentum from moving through the hot air would cause your velocity to be greater than the projected terminal velocity in the new, more dense air. Depending on how fast the air slowed you down, and how fast you were going when you entered this more dense air, you could even remain above terminal velocity for a while. In this picture, the orange arrow points to the point where Felix begins moving faster than terminal velocity, and the bracket shows the interval on which he was moving faster than terminal velocity, which is about 50 seconds. In conclusion, we see how drag varies from fluid to fluid dependent upon density, which in turn is dependent upon pressure and temperature inside that fluid. We also see how terminal velocity can be exceeded given certain special conditions. Newton's second law tells us that the rate of change of velocity is the sum of forces divided by mass. In our case, the net force is a result of the weight and drag forces. Even though this net force causes Felix to slow down, even when he passes terminal velocity, the terminal velocity is decreasing faster than his velocity is, which allows for him to stay above terminal velocity for a good portion of his flight. Thanks for watching.